Alright everyone, and welcome back to the final and practical session of our deep learning workshop. First of all, congratulations. Over the last 5 days, you have learned concepts that many students didn't encounter until much later in their engineering journey. Let's quickly look how far we have come. So on the first day, we understood the artificial intelligence, the machine learning and deep learning being the subsets of artificial intelligence and neural networks. On the second day, we explored much of mathematics behind the learning, including the vectors and matrices, along with activation and loss functions and gradient descent. On the third day, we opened the neural networks and understood the perceptrons, the weights, the forward and the backward propagations, and batch sizes. On the fourth day, that is yesterday, we saw how the machines see using the convolutional neural networks. And today we are going to combine everything into a Capstone AI project. This is exactly how real AI engineers work, not by memorizing the definitions, but by building systems. Today's goal is going to be pretty much simple. We are going to create an AI that can look at an image and identify what it contains. By the end of this session, we have a trained CNN, an image classifier, a deployed web application, and your first end-to-end deep learning project. Dive in. The very first thing every AI engineer does is prepare his environment. Today, we are going to use Google Colab. One of the biggest and advantages of Google Colab is that it already comes with most of deep learning libraries installed. However, for our projects, we need few additional packages. Let's install them first by running pip install. So let us install few libraries first. I'll write installing libraries, and in installing libraries we will make a code block which says install pip install few libraries such as TensorFlow. We have to put an exclamation mark before pip so that it installs. Then we need TensorFlow dash datasets and Gradio. And for if any question is asked, we'll have to counter it as well. So I'm running this particular cell in which the libraries will get installed. The first one being the TensorFlow, the second one being the datasets which are derived from the TensorFlow, and the third being the Gradio. Now exactly what are these? TensorFlow is our deep learning framework, the toolkit that we discussed in our first practical session. The TensorFlow datasets allow us to access datasets directly from the internet without downloading them in our local environments. And Gradio helps us create AI applications without writing for front-end code. In real companies, entire prototypes are built using tools like these. Now let's import everything. Let's import first of all the TensorFlow, the NumPy, Matplotlib, and the Gradio. So let's start by writing import TensorFlow as TF, then import TensorFlow underscore datasets as TFDS datasets. Then we need to import NumPy as NP, then import Matplotlib .pyplot as PLT, and finally import Gradio as GR. Okay, now students often ask, why do I need to memorize these imports? The answer to this question is pretty much simple. The answer is no, you don't need to memorize these installations, but over time you will naturally remember the important ones. The goal is to understand why we are using them, not how we are using them. The TensorFlow is used for deep learning, NumPy is for numerical computation. The matplotlib is for visualization purposes, by which we can draw graphs, we can visualize the graphs or charts and all. And Gradio is for deployment purposes. So let us run this particular cell block. Yes, it has completely been run without any errors. If there were errors, it would have been shown on this part. Okay, now we will load the data set. So data set load. Okay, and in this I'll have a new code block in which we will be writing about few steps in which we can download the dataset from TensorFlow datasets. So this is the very interesting part. Notice that we are not downloading the dataset manually. There will be no zip files, there will be no folder organization, no dataset cleanup, everything. Everything is provided by TensorFlow datasets and it handles everything. We just have to load the dataset as training and testing using the TFDS. So when we execute this particular line, so let me write the code for that, which is going to be ds underscore train. Then we have ds underscore test and ds underscore info. Okay, that is going to be tfds dot load, and in load I'll have to write about tf flowers, TensorFlow tf underscore flowers, and in this we will be writing split as in we are going to give 80% for the training and 20% for the testing purposes. So for that I'll have to write first for training split, and in split I'll have to write first the x part, that is the training parts inputs, then the training parts training parts outputs. So that is going to be train, and in train I have to write here 80%, okay, and again I'll have to write comma, and here train, and here again is to 80%, yeah, that's pretty much done then. And as supervised, so this is supervised learning model, supervised, it is going to be true, and also we want it with info equals to true. Okay, so this is pretty much done, and let us run this particular line. Okay, so when we execute this particular line, TensorFlow automatically fetches the data set from its servers. This is exactly why cloud-based machine learning has become so popular. Instead of spending hours managing the data, we can focus on building the models rather than that. The data sets we are using contains flower images. Each image belongs to one of the 5 categories like daisy, dandelion, rose, sunflower, or tulips. And think about what this means. A machine learning is not going to distinguish the flowers only using pixels. No human written rules. We have no hard-coded instructions, pure learning. And now let us move on to understanding the data. So for that, we first need to write the information that we have gathered from this. So that is going to be class underscore names equals ds underscore info dot features and in this I'll have to write the labels label dot names. So these are going to be the outputs, basically class names. Yeah, and print, and in print I'll have to write about classes, and here class underscore names. Okay, control enter. Yeah, there are 5 different classes: dandelion, daisy, the tulips, sunflower, and finally the roses, as we can see. Okay, now we will move on to start with the pre-processing work. So these are the class names. Now we can see all the available categories, our output space. When the model finishes training, every prediction must belong to one of these 5 classes. The machine doesn't understand the flower, its structure or anything. It only understands the categories. And our job is to teach the network how to connect images into categories. Now we will start with the processing. So I'll write here pre-processing, pre-processing, and in pre-processing I'll give the image size img underscore size equals 128, small img size equals to 128. Okay, then I'll also need the batch size batch underscore size, and batch size, let's say I have kept it to 32. Now I'll have to define the pre-processing mechanism. So function of pre-processing, in which I'll be taking images and label, and in that I'll have image which will be resized tf dot image dot resize, and in this I'll have image image size by image size. So this will be img underscore, okay, size comma img underscore size. So the image will be loaded in this particular format. Since image size we have defined as 128 pixels, so the image will be loaded as image comma 128 pixels by 128 pixels, and batch size we have set it to 32. Now next step is to define the uh, color gradients. That is, image will be divided over 255 parts. That is the pixel total number of pixel colors in grayscale, and return image and its label. Okay. Now we will be writing about training and testing. Okay. So that will be train underscore ds, which is ds underscore train dot map it up to preprocess. Okay, and then test underscore ds, that will be equal to ds underscore test dot map up to preprocess. Okay, and finally we also need train data sets and shuffled it over some batch size or particular size. So that is going to be train underscore ds is going to be train underscore ds dot shuffle up to 1000, and same train underscore ds, it is going to create now batch size. So that is going to be train underscore ds and then the batch size. Okay, the batch size. Similarly for test as well, test underscore ds equals test underscore ds dot batch, and in this batch underscore size. Okay, so this is pretty much done. Now control enter, let us see what it gives. It gives that there is a error in image size. Okay, so image size, Okay, so the error has been cleared, and now we move on with auto tuning as well. Okay, so in below this we'll have to write train underscore ds equals train underscore ds dot prefetch, and in this tf dot data dot auto tuning auto tune. Okay, and I'll have to copy this for the testing as well. So instead of train, it is going to be test, and here as well it is test. Okay, so let us run this again. uh Auto tune feature is not present, it seems. Okay, there is going to be equals. Okay, my bad. There is no attribute named auto tune, it says. Okay, train underscore ds equals train underscore ds dot prefetch tf dot data dot autotune. Hmm. Okay, so the error has been cleared now. Now we are going to display some sample images so that we understand that we are working on the right code or not. So sample images, okay, and in this I'll have to write a code in which I'll be describing a plot or figure. So plt dot figure, figure, okay. In this I'll have fig size, let's say I'll keep it 10 comma 10 10 comma 10. Okay, now next is going to be for image comma label in ds underscore train dot, let's say I take 9. Okay, and in this is a loop. Okay, so let us specify that it is a loop in the next line. Okay, so in this I'll plot it. So plt dot subplot, and subplot is going to be 3 comma 3, let's say, and the label dot label dot numpy is going to be the array plus 1. Okay, and then plt dot im show image show. In this it is going to be as image dot numpy image.numpy. Okay, and dot as type. Now I need an encoding I need uint8. Okay, and after this I'll plt dot title and in this class underscore names will be labeled as label, and next plt.axis. Now this axis should be off. Okay, and the last but not the least, I'll have to give a title layout, plt.title underscore layout. Okay, and last is plt.show. So we are here visualizing few of the images. Okay, we are using this particular command, that is plt.imshow, in which the images are going to appear on our screen, and as humans we definitely, like, we are immediately going to recognize those images. Okay, there seems to be some problem in the first line. Fig size equals, yeah, we are going to definitely, like, immediately we are going to recognize the images. But remember that what we learned on the fourth day, the machine is not able to see these images. It only sees the matrices. Every pixel is just a number, and every image is just another representation of mathematics. CNNs converts these images into meaningful patterns, And that's exactly what we are going to teach the model. Now, as we talked about the pre-processing step that we did here, so this is pre-processing. The first thing we do is about resizing each and every image. Why? Because the neural networks requires consistent input dimensions. If one image is 300 by 300 and another is 1200 by 800, the training becomes difficult. So we are going to standardize them. Next, we pick up the normal pixel values. In the second day, we discussed why neural networks learn better when the numbers are smaller. And pixel values are going to range from 0 to 255. And then we are going to convert them into zeros and ones. This makes the learning faster and more stable. Now we arrive at the heart of today's project, that is building the CNN. Okay, so here I'm going to write about build the CNN. Okay, building the CNN network, that is the convolutional neural networks. This is where all four previous days come together. So now let's look at the architecture. Let me create it. So I have to write here model is equal to tf.keras.sequential, and in sequential I'll have to write square bracket tf.keras.layers dot conv 2d. Okay, and in this I'll have to write about let's say 32. Okay, and then the size is 3 comma 3, and then okay, yeah, and then activation is set to relu, and input underscore shape, it is going to be 128 comma 128, and divided over three different channels, that is R, G and B, red, green and blue. Okay, so this is the basic first layer that we have made. Now we move on with the second layer, which is tf dot keras dot layers dot max pooling max pool in 2D. Yeah, max pooling 2D, and then finish it. The third layer is again going to be the convolutional layer. So tf dot keras dot layers dot conv 2D. Okay, and this is going from 64 comma 3 comma 3, and then the activation equals relu. Okay, and the next is going to be comma and enter. The next is going to be again the max pooling layer, then again the convolutional 2D layer, and it goes on. So let me just copy these two lines so that I don't have to write them again and again. Okay, so this is going to be the same, and instead of 64 I'll have to write 128. Yeah, and then again I have a max pooling layer to be attached. So these can go on n number of times, as much as we like them. The more they go, the more the layers are going to learn. The image is going to learn on the layers. Now finally we are going to flatten it. That is tf.keras.layers dot flatten. Okay, so that the layers stick on one another. And last is tf dot the dense layer that we are going to add for it. Okay, so the next layer is going to be tf dot keras dot layers dot dense, and that is going to be 128 comma activation equals to relu. Okay, and next we are going to write the dropout tf dot keras dot layers dot dropout, and dropout layer is set to 0.3, Then again let us add a dense layer, the final layer. Okay, so again, so instead of writing the whole thing, I'll just copy it from here, paste it here. Okay, so the layers, the dense, and here I'll have to write length is as per the class names, class underscore names, and activation is set to softmax. So control and enter, and it has given all the layers to it. And let us first of all print the model summary, model dot summary. So this is the model summary. First of all, convolutional 2D layer, then max pooling 2D layer, then convolutional 2D layer again, followed by max pooling layer again, then again the convolutional layer, max pooling layer, finally the flattened layer, then continued by dense layer, dropout function, and finally again the last dense layer. So there are total of 3 million parameters that our model is going to train on. Okay, so now we compile the model using Adam optimizer and sparse categorical entropy. So I'll just write it here only instead of writing in the next code block, model dot compile. We are going to write optimizer as Adam, and loss is going to be sparse underscore categorical underscore cross entropy, comma, and finally metrics is going to be the accuracy. Now we will print the model summary. So yeah, the whole the compilation model has been done. So now these are the architectural layers that we are going to work on. So these structures may look a little bit intimidating, but we have already understood the importance of each component. The convolutional layer acts to extract the components, okay, or the features. Then we have the pooling layers which reduce the dimensionality of the images. Then the flatten layer which converts the feature maps into their vectors. They combine all the layers. And last, the dense layer which performs the classification function. So these all things were discussed in day 4. And in day 4, we also talked about images, the convolutional networks or convolutional layers. We also discussed about ReLU, the ReLU function, activation function. Then we also looked at all these layers such as pooling, dense, and from that we predicted. And that's exactly what we are planning to do here today as well. In the compilation, we understood 3 major things. The first one was the optimizer, for which we used Adam. In the loss function, we used the sparse categorical cross entropy function, and the matrices were the is the accuracy function. Okay, so Adam is the version of gradient descent which helps the network to learn efficiently, and loss function measures the mistakes, and accuracy tells us how often the model is predicting the values correctly. And without these 3 major components in the model compilation, the learning cannot really happen. Now we will move on to the main part, which is training the model. And for training, we will write the code in which history will be defined as model.fit, in fit train underscore ds, comma, validation underscore data will be represented as testing data, test underscore data. Okay, and we will run it for epochs equals to 5. We will run it for, let's say, 5 epochs. Okay, control enter. So here AIN. Okay, test underscore ds Yeah, it is running with the first epoch. It is going to take some time. Until then, we will write code for our evaluation matrix and the accuracy graphs as well, so that the time will be saved in that matter. Okay, so let us begin with the evaluation matrix. So evaluation, evaluation, and in evaluation, I'll write a new code block which says about loss, comma accuracy equals model.evaluate test underscore ds. Okay, and print the final accuracy, print the final accuracy as print the final accuracy as accuracy. And then we will also be plotting the graph, and to plot the graph we will have to first of all specify the figure size. So plt dot figure, and in this I'll have to write fig size to be set to 8,5, let's say. And plt dot plot, we'll have to plot the graph based on history dot history, and in this I'll have to write about accuracy comma label equals the training accuracy. Okay, now we will have to plot another one in which we will be having more validation accuracy as well. I'll just copy it and I'll paste it here. plt history and history. I need here validation accuracy. Here as well, I'll be writing validation accuracy. Okay, so by this we will be able to write about the validation accuracies and the training accuracy as well. Now we will move on to plot the x-axis and y-axis. So plt dot x label label, and in this we will be writing about epochs, and plt dot y label. Here it is going to be about accuracy. And plt dot title, the title is going to be training versus validation accuracy. I also have to plot the legend, plt dot legend and plt dot grid, since we need the grid. And finally we will write about plt dot show. So this is going to show us the plots. So now let us recheck if we have completed. Okay, so the second epoch is running. Almost 50% has been completed. We have accuracy of 54%. I hope it goes above at least it goes about 60 or 70%. Now we will be writing about the next code. So let us write the code to save the model. Save model, in which we will be writing model dot save, and it will be saved in the form of flower underscore classifier dot keras. So imagine spending hours training a model. Would you like want to train it again and again every time? Of course not, it is going to be a hectic process. So that's why we need to save the model using model.save function. Now our trained intelligence is going to exist as a file. And this file is going to contain everything like weights, the biases, the learned patterns, the knowledge that it has gained, and we can deploy it anywhere we want. Okay, so now we are going to write about the next code, which is about like testing it on random image. Okay, so this is about saving the model. Okay, I guess I made a mistake here. I had to use a text box. Yeah, yeah. Now we will test the predictions on random image. Test randomly. For that, I'll add a code. Or let's rather than testing it randomly, let's build the Gradio. Let's build the Gradio application. And in this, we will be defining the classification classify underscore flower as image. And in this function, image is presented as tf dot image dot resize, and in this it is going to be image comma 128 comma 128. So 128 by 128 pixels are going to be fetched from the image, and again the image is going to be just like how we presented it in the earlier this. We are going to present the same image in 255 pixel format. So image equals image divided by 255.0. Okay, again image is equal to numpy dot expand underscore dimensions, expand the dimensions as image and as per the axis. Then we will move on with the predictions. So prediction will be model dot predict and in this we need to have image and the verbose. Image and the verbose, that is set to 0. Okay, now we will also need the predicted class to be present. Predicted class which is defined as np dot argmax maximum arguments. The class which will have maximum arguments, it is going to be presented as the flower from that particular category. So that is argmax, and in bracket I'll write prediction. Again we will calculate the confidence as well. Confidence, and it is presented as np dot max of prediction, and the finally it is going to return as class underscore name, and in this we have predicted underscore class, and here float of confidence. Float of confidence. Now, finally, we need to host our application, and for that, we need to write a function by which we will be able to give the commands for that as well. So I'll have to write here. It seems there is going to be problem in this part of code. Let us classify that. So first, let us check how much. Okay, 5 on 5 epochs are being done, and the accuracy is almost 74%. Let us wait here to finish everything so that we can move on to the later part. It is going to take almost 45 seconds more, 40 seconds more now. So this type of example can also be taken on the other level of using it in medical devices, let's say, or meteorological data sets. By using it on meteorological data sets, we can predict whether there is going to be rain. If there is going to be rain, how much amount of rain is going to be in that particular areas. If it is in falling in rain prone areas or desert prone areas, like this we can do the classifications. Okay, we have attained the accuracy of 74 and 80, 74.80%. Now we will move on to running the evaluation function, and the evaluation function is running. It is gathering the accuracy of 67%, I guess. Okay, this is the evaluation function that it has run upon. The accuracy, as we can see here. Now we'll have to save the model as Keras, and let's check where we, okay. Yeah. So by this we have completed our the we have created our function to classify the flower or the image of flower, and now we will move on with launching the app. For that we will need to specify the app basics. So app equals gradle.interface. So that is going to be gradle.interface, and in this interface we are going to provide the function that is about classify underscore flower, classify flower. Then inputs are going to be the images, that is gr dot image. Okay, then we are going to need the outputs. So outputs are going to be gr dot label and title. The title is going to be, let's say, uh, AI flower classification. AI flower classification. Okay. And then we also need some description for it. Description. So let us ask the person to upload a flower image, and CNN will classify it. CNN will classify it accordingly. And then let us write about launching the app.launch, and the app is going to launch itself. When we run this, is giving me some error. Okay, there should have been a comma here again. Control enter, and it looks like we are running Gradio hosted on Jupyter Notebook, which is Google Colab Notebook, but obvious. And the public URL, it has been given, so let us go on this particular URL. It is also, so now let us see different types of flowers. By putting what kinds of flowers are we getting what results. So let us first of all start with tulips. So here I have few images of tulips. Let us grab one image. I like pretty much like this image. So I'll grab it here in this. I'll drag and drop it. Okay. So it is going to, when I click on submit, it is going to predict me the image. It is giving me 77% accuracy for the word tulips. Let us take it with some another flower as well. Let us take the sunflower. Okay, so I like this flower. Okay, let us take this particular flower. I come on the website and drop it here. Yeah, this sunflower looks better. Submit. It is giving me 93% accuracy for the term of sunflowers. So that's how we are predicting the flowers using our AI classifier. Up till now, we have been working inside the notebooks, but real users don't use notebooks. They use applications. So we have built one application in which we have used this particular Gradio. So let us check. This is the application that we have built, the same application on which we performed right now. Okay, this is the same application that we have built on Gradio, and it allows us to create AI interfaces just like within a few lines of code. No HTML required, no CSS, no JavaScript, just Python. We have created a function called classify flowers, and in that classify flowers we are moving the image. It processes the image, runs the prediction, and returns us the results. So let us take one more tulip flower. Let us take this flower, drop it here. Let's take it again. Yeah. So this is the tulip flowers. Submit. It predicts 99% tulips. Okay. So this is the thing about the classifiers. So we have launched the application, and just like that, it opens in our browsers, and we have working AI application that you can paste it in your CVs. The CNN is going to process them. The predictions appear super instantly, and this is exactly how many AI prototypes are built in the industry. You started just a week ago by learning what AI is, and now you have deployed one as well. That is an incredible journey. Today we have built CNN, an image classifier. We have also trained a deep learning model, and we have deployed a web application. This is end-to-end AI pipeline. More importantly, we connected everything we have learned so far across 5 days. The day first gave us the foundation, the second gave us the mathematics behind deep learning. On the third, we explained how neural networks work. And the fourth day was about showing how machines process the images. And today, the fifth day, we transformed these concepts into real life applications. That is exactly how the engineering works: learn, understand, build, deploy, and again repeat. And with that, we officially conclude our deep learning workshop. I genuinely hope this workshop helped you understand AI is not just any another magic. It is mathematics, engineering, and creativity working all together. If you enjoyed this series, please like this video, share it with your friends, and subscribe to my channel. Leave your doubts and questions in the comment section below so that I regularly go through student feedbacks and try to answer as many questions as possible up to my knowledge. Also, don't forget to explore Ingiverse. All recordings, certificates, and quizzes, along with notes and future courses, will be available there. And if you like to see or continue learning, check out my YouTube channel Sahil at Work, where you will find contents on algorithms, problem solving, data science with Python, and other signal processing applications as well. And there are many more engineering and technology topics I am building on. Thank you, everyone. Keep learning, keep building, keep experimenting, and most importantly, keep creating the future. See you in the future courses. Up till then, take care and have a good day. Adios.